can see the problem on the top left. There's a frictionless pulley. It takes the shape of a uniform solid disc. It's right here. Okay. And you're going to have and on top of that, you're going to have a stone over here that's pulling it down. Okay. And they tell you that they want to know how far down it's fallen, how far down this way it's fallen. If the pulley has 4.50, sorry about the lack of point, 4.50 joules of kinetic energy. Okay. So if we take a look at it, as it's fallen, initially when it hasn't fallen, it has lots and lots of GPE. And that energy goes and becomes two things as it falls. We're going to call the energy at the bottom, at the point that we're looking at when it has the 4.5 joules, the bottom. It doesn't have any GPE there, we're going to say. And we're going to say that at the bottom, it's going to have two types of energy. It's going to have kinetic energy in the stone. That's going to be translational. And then it's going to have some form of rotational energy, maybe. That's going to be in the pulley. And we can make an equation of that. The equation of that is going to be mgh is going to equal 1/2 mv squared. You'll notice that I actually left the same m for both of those because the m that's dropping is the stone plus 1/2 I omega squared, and that's going to be for the pulley itself. Okay. But if you notice we have a V and an omega, that can't possibly stay. So we're going to replace V with R omega. So we're going to have mgh equals 1/2 m, and I'm going to replace the V with R squared omega squared plus 1/2 I omega squared. Okay. Well, we can find the radius is given to us, the mass is given. We can actually probably find the moment of inertia for it pretty easily because we know the mass and the radius for the pulley. But the thing we don't know, and the thing that would be most helpful would be to find that angular velocity. But they tell us the energy, so it won't be too bad. So let's do that over here. So let's find omega using the energy. So we're going to say 4.5 joules equals 1/2 I. Well, it's a solid disk, so it's going to be 1/2 times m. The mass of the disk is 2.5 kilograms. And omega, and R squared is going to be 0.2 meters quantity squared. So we got I and omega squared. Okay. So if we solve all that stuff out, boy, it looked kind of ghostly and yucky there. We get an omega of 13.4. It really looks like 13.4 over seconds, but we know that's radians per second. Okay. Then we put that back in over here, and I'm going to start to substitute all of our numbers in. So 1.5 kilograms, 9.8 meters per second squared times h equals 1/2 1.5. Remember, it's the same stone. 0.2 meters. Doesn't much like O or point. Okay, and that's going to be 13.4 radians per second. I'm going to write plus 4.5 joules. There's no need to recalculate all that stuff. They already tell us it's 4.5 joules. Okay. So when we do that, this whole thing here when you calculate it, turns out to be 5.39 joules plus 4.5 joules, and this is going to be 14.7 newtons actually, times the height equals that. Okay, divide both sides by 14.7, you get a height of 0.67 meters. Part B of the problem asks what percent of total energy, total kinetic energy, does the pulley have? Maybe we can do that. Okay. Well, we already solved for most of it. We know that the pulley's energy, they tell us in the problem, is 4.5. And we actually know the total energy that's in the both items. It's going to be the energy in the pulley plus the energy that's in the stone. We figured it out in the last problem, 5.39. It's going to be the 1/2 times 1.5 times 13.4 squared times the radial velocity times, or angular velocity, times 0.2 squared. So if we take all those, divide it out, we get 45.5%. That's how much of the energy is left inside of the pulley when we're done.